Hi and welcome back to a new video. On my table we have the Danamics LMX air cooler, which is a liquid metal air cooler. It's quite unique, quite special. It's from 2010 and it's probably the most dangerous CPU cooler ever made, which we're going to check out in today's video. If you take a look at this cooler first, it might appear as a normal heat pipe air cooling unit because the setup is pretty much identical. We have cooling fins and in between you can see something that looks like heat pipes. But in this case, the heat pipes are not filled with water. Typically, heat pipes are filled with water at decreased pressure, so the water evaporates and then condenses again at the cold area, probably up here around the fins. That's how heat pipes work. But in this case, we have copper pipes that are filled with a liquid metal. And Danamics back then in 2008 thought that this might be a superior way of improving coolers because in their opinion, they seemed to be limited by the capability of transporting heat away with the heat pipes. So they started having the LM10, which was kind of released in 2008, but not to the public. They sent it to some reviewers and the performance was kind of disappointing. So yeah, Danamics said, okay, we will go back to the drawing board and improve the cooler, and that's how the LMX was born. The LMX was sent to reviewers about March 2010, February 2010, and by around August, September 2010, Danamics as a company was liquidated. Which doesn't mean necessarily that they went bankrupt, but probably they didn't see any kind of business opportunity anymore, so they shut down their company. I'm not even sure if the LMX ever officially went on sale in shops or if only a small quantity made it. It was always very hard to find apart from the reviewers who had them. There were a few circling around on some like eBay and something, but I always tried to find one, never managed, and then Tori reached out to me via email last week and said, hey, I found this in my basement, and I said, that's amazing, can I please have it and test it? So that's how we ended up here. As you probably already noticed, this cooler is not in the best condition, and Tori also didn't know if it even still works or not. But first look, as I said before, we have all those fins to dissipate the heat, and in between we have the pipes that look like heat pipes, which they're not. And also just a normal nickel-plated copper base. If we take a look on the top part, then you can see typically a heat pipe cooler would just end directly on the top fin right here. But these pipes extend further. I will try to remove the cover in a second so we can maybe take a look inside. Plastic cover is gone, but you can see there are wires up here. And compared to an air cooler, this entire thing on the top is completely unique and different. Because up here we have electromagnetic liquid metal pump, which will be responsible to have some kind of flow inside those pipes to circulate the liquid metal inside. So the thing is, even back then I was reading news articles and reviews about both LM10 and LMX, and I was just reading the liquid metal part and I kind of thought in my head that it was gallium-indium alloy, even though it was already stated back then that it's not. Then yesterday I thought, wouldn't it be interesting to cut this open and see what the state is inside, how the pump is built, and I don't know, after 10 years what the state of this liquid metal is. And then I was quickly talking with Tori, asked about if he has some kind of access to a manual, found it, and yeah. Then on the first page I was greeted with a huge amount of warnings, like if a small amount of the liquid metal escapes, then you have this, then you have to do this and that. And if a big amount of liquid metal escapes, be careful because it will self-ignite, and don't try to extinguish it with water because then it will explode. And I was like, why? This seems odd, because in my head I was still thinking about gallium-indium. And then continuing reading, I found out that inside is a sodium-potassium alloy, which is certainly interesting because I'm not sure how it went for you, but for me at school, I don't know, like 5th, 6th grade, when we had basic chemistry, we were experimenting with the alkali metals because both sodium and potassium are alkali metals and they are highly reactive. If you throw a small portion into water, you have those like impressive explosions, and that's inside here. I'm not sure why they thought it would be a good idea to do that, and I can also promise you after I'm done shooting this video, it will not end up in my basement. I will make sure that it will be removed from my apartment, because I mean, just imagine you drop this on the floor and it cracks somewhere and then all this stuff comes out and burns your house down. Not so sure about that. And also, generally speaking, I'm not even sure why they picked this, especially also over water. I'm not even sure if it's better, because the heat capacity of sodium potassium is about 1/4 of water. So the heat capacity is how much energy in joule or kilojoule you need to heat up a material of 1 kilogram by 1 degree Celsius or 1 Kelvin. And the heat capacity of this specific metal alloy is about 1/4 of water. So it can take 1/4 only of the energy to reach the same kind of temperature change. At the same time, the thermal conductivity is a lot higher. It's about 30 times higher than of water. But typically in this like transporting heat scenario, it's the same with the water cooling loop. Water is superior because it has a very high heat capacity, not that high thermal conductivity, but that's not necessary, because thermal conductivity would describe the heat transfer within the material, which is something we don't really care about in this scenario, because we only want to remove the heat and take it up and not conduct it within the material. So yeah, the entire material choice is quite odd. I also want to point out that I have no clue if this thing still works. There is also this controller board included, which looks kind of like an inverter. It's powered by a 4-pin Molex, and also I'm not even sure if that was a review unit or like an early sample, because just looking at the connectors, already those are different from what you can find online in reviews, because they had like a normal connector to plug in, whereas I have to kind of figure out where they go and which polarity. It could also be that polarity doesn't matter and that it would just pump in the opposite direction. That is something I have to find out. And when it comes to mounting, this is kind of similar. It's very close to socket 1700. I think it was made for maybe 1366. So that's quite close. I bent it a little bit to shape so we can mount it on a recent 1700 socket and see if we can get it to work. I did some basic measurements to just check if there is a short somewhere or some like catastrophic failure on the PCB, but like in between the MOSFET and like those caps here, in between the output and everything, there was no short. All the values seemed realistic, so looks kind of okay. And also I think polarity should not really matter. I mean, if it's a normal electromagnetic pump, then might just spin the opposite direction. So I will attach it just on here. Then we will attach it to the Molex and see if there's anything we can figure out. In addition, I also now added current clamp, simply to see if whatever is going on, if something is going on, because it could also be that you cannot even hear anything of the pump. Not fully sure, to be honest. I think I heard some kind of a clicking noise at the beginning, but we have a green LED on the PCB, which looks good for power. There's also one for temperature, which does not light up, so that should be fine. We can also read that something is going on, because this current clamp translates 1 millivolt every 100 milliamp that are flowing, and we can currently read 300 millivolt. This means if we translate the current clamp of 330 millivolt roughly, which is 1 millivolt per 100 milliamps, that means currently we have about 30 amps flowing across those cables, which also explains, first of all, why they have to be rather thick and why they are so warm. It's insane. Like, that's surely something between 40 and 50 degrees Celsius. It's really warm. Not sure if it's supposed to be this way. Didn't find anything about this online, about unusual cable temperature, but I mean, they probably made them beefy for a reason. And we will, because I have no clue if this is like working or not, we will simply double check. I have a test set up with a Noctua air cooler. We will run one benchmark or like a game, see what kind of baseline temperature we will have, and then see if this works, and if yes, how good it is. Also, there was never a fan included, so you always had to use your own 120mm fan, but I think we can just try to put the Noctua fan on top. For a quick comparison, I tuned the 12900 KS to 5 GHz, 1.25 volt in idle. Will definitely drop down under load, as you will see right here. So it results in a quite, I would say, good power draw of about 200 watt. and the Noctua U12A can easily handle that. Typically temperatures somewhere between 80 and 90 degrees Celsius when it comes to the P-core temperature. In the gaming scenario, obviously the temperatures will be much colder. I first waited about 5 minutes for the cooler to reach a steady state when it comes to the temperature. And we typically see a temperature on the cores right now of about 40 to 60 degrees Celsius, I would say, on average. So that's definitely quite a lot lower than what you would see in Cinebench as usual. Finally, managed to attach the cooler. And if you think this looks crappy, then I totally agree with you. The thing is, with this LMX by Danamics, I had to remove the plastic shroud on the side because I just reassembled it, but then figured out that the plastic shroud just collides with the VRM cooler, so I had to remove it. Now I have to figure out a way how to put the fan on top, but I think I will just use some probably zip tie, something similar, to just hold it in place. Then wiring goes to the controller board, and that's pretty much it. Now, just a question if the cooling works or not, which is hard to tell. And then what about performance? Okay. As usual, if there are no explosions, no fire, no smoke, that's already a very good start. Well, at least I think in idle should be working fine, because with the 12900KS at that speed should definitely be warmer if the cooler was failing. And like just judging by touching the copper pipes and also the top part, easily 35 degrees Celsius. This has to be working. That's great. Now pretty much same gaming scene, also waited another 5 minutes to get some heat into the cooler first. But as you can see, this looks pretty much identical to the Noctua cooler. Just in terms of raw temperatures, we're also looking at somewhat between 40 and 60 degrees Celsius. And I mean, that's not a perfect comparison, but yeah, simply because of the changing gaming load all the time. But overall, I would say that's totally a usable cooler, even though back then when it was launched, it had pretty bad results, I would say, but also mainly because of the price back then compared to now. This cooler was extremely expensive, about $120. Same scenario, CPU is still in the same overclocked state, same voltage, same clock, and we will rerun Cinebench now. Power draw, as you can see, it's the same, just above 200 watt. Now under load, it looks pretty similar to the Noctua cooler, but maybe 3 to 4, worst case probably 5 degrees Celsius warmer than the Noctua cooler. But considering how old it is, that's better than I expected. I have to say, I was surprised when it comes to performance, because back then, watching the reviews, most of them were not that good. And especially because if you compare it to the U12A, which is one of the best air coolers you can probably get, this was not too bad. It's like 4 to 5 degrees Celsius worse. But then again, I mean, if you think back to 2010, the average air cooler price was quite a lot lower. So this was fighting against coolers that were half the price and could often outperform this cooler. It just doesn't make any kind of sense. It just shows that the heat pipe overall is definitely superior to filling this with potassium-sodium alloy, which also, I mean, it has a lot of dangers to it. I would personally never use a cooler like that in my system. I think steady state, it's probably fine even if you store it. I don't expect that something would happen, but I also have no experience whatsoever when it comes to corrosion of a block like that. Whereas if you look at a simple heat pipe cooler like this Noctua one, it's a mount and forget solution. It will not degrade over time. You know what a heat pipe is, it's not dangerous. And yeah, so it just makes sense that it never established itself in the market. And I think if it was a mass product, then we would maybe also see problems. Then, I mean, if you have millions of units on the market, then once in a while something will happen that, I don't know, you transport a lot of these in a truck, and then the truck has an accident and the stuff comes out, and then that's when things becomes interesting, which is where in normal water cooling or air cooling, you will never have these kind of risks. And that's probably why it's good that this cooler never made it as a mass product to the market. But it was definitely an interesting thing, interesting concept to see that you can have a cooler which is circulating sodium-potassium alloy all the time, and it also works after this long time sitting in someone's basement and was never touched, that it's still working today. That was interesting for me, but also it's time to remove it from my apartment. Thanks for tuning in. See you next time. Bye bye.